Hello, my name is Pablo Vaquero, and today I'm going to present my project in bridging the Grand Canyon Gap. So, in this presentation, I will talk about the materials selected for the construction of the bridge, the testing of the mechanical properties of these two materials, then the construction process of the bridge, and finally the innovation I included in my project. So firstly, I will talk about my first selection, which was biocomposites. Um, in specific, I will talk about hemp and flax fibers. The first advantage is that they are environmentally friendly. This means that they are degradable over time without emitting certain gases or substances that may be poisonous for the environment. Also, they have an advantage over synthetic composites, and it's the low cost of producing them due to a reduction of the 17% in the energy used for production. And also, they are very lightweight, which is an advantage for the specific strength of the material. Then, talking about matrix composites, we need to highlight that their mechanical properties depend on certain characteristics of these matrices, such as the matrix interface or the orientations of those fibers. To the right of the presentation here, you see that the force needs to be aligned in a certain direction. If the force were aligned perpendicular to those fibers, the tensile strength would be reduced highly, and of course we do not want that. So the orientation is a key factor also in the biocomposites. As I said, their mechanical properties are not so good compared to synthetic composites, but they are relatively good enough for the project we are interested in. And finally, another advantage is that they can be shaped into many different forms and can have many different applications. Regarding my second material was advanced ceramics. I wrote some examples like alumina, zirconia, and silicon carbide, which are great for this application. Why? Basically due to their high hardness, strength, and toughness. Also, they are not conductive, and drawback is that they are brittle. They are more brittle than than some metals used in construction, such as steel. However, they've got some positive things, which is resistance to those high temperatures and corrosion, and also they have a great fatigue resistance, meaning that they can withstand a lot of cycles. Cracks usually appear, but that is not a problem because they tend to appear late in the cycle plot to the right of the endurance limit we want to reach. So they're usually not a problem. But well, it needs to be tested as well. And also another important thing is that they are really easy to manufacture in complex shapes using, for example, 3D printing. The drawback is that they are usually difficult to join them, but I've come with some possibilities for this last drawback. And another thing that is also important is that they are more expensive than biocomposites. This is also important because we need to take also cost into account when designing the bridge. Okay, so now talking about the different types of tests, we have the compressive strength test, which is basically the machine we saw in class. The material is pushed with the downward and upwards forces, and then we can handle the data. This is for a biocomposite, that is why it is shown in green. Okay, this will be the same throughout the presentation. And regarding advanced, well, we can see the yielding point, the yielding point, the ultimate compressive strength, etc., the elastic, plastic, and failure zones. And this will be the graph, at least something similar to what an advanced ceramic would be. Okay, much lower elongation between both of them, caused by the brittleness and ductility difference. Okay, so now regarding fatigue strength, basically the sample goes here, as you can see in this sketch, and a sinusoidal signal of stress is applied to see the different endurance limit of both materials. Okay, so for the creep resistance, we usually apply either a compression test or a tensile test, and usually under the application of some heat. The thing is that we usually apply loads that are below the yield stress point, so to be in the elastic region, and this will lead to a smaller deformation, but over time this deformation will lead to a higher deformation. Okay, so regarding the biodegradability of biocomposites, what I would do is to submit the biocomposites to oxygen, water, high changes in temperature, and other chemical compounds to see their effects. For example, does it oxide? Is it this decomposition? Is there a reduction in the mechanical properties? After observing this, I would probably try to see which coatings fit better. There are many coatings that are usually used for avoiding corrosion, um, and I think that that is an important factor to be tested in the lab before implementing it to the bridge structure. In the other hand, as we mentioned before, the advanced ceramics can be created using 3D manufacturing. Uh, the only bad thing is that they are difficult to join, and that is why I think we can use bioresins, which are usually good to fix or to join different parts. And well, as we have been talking with biocomposites, I think it's a good idea to introduce also the fact that bioresins could be used in order to join the parts made through modular construction. Now we start with the testing of our materials. The first test is the hardness test. I would basically perform two different types of tests depending on the material. For advanced ceramics, I would choose the Fresnel test. You can see that the denture is circular shape. This is the most common type of machine used, as we were shown in the lab. Why Brinell? Basically because advanced ceramics are much harder than biocomposites, and the values of hardness usually go between 1500 to 3500. This would be a good measurement. Maybe Rockwell is a bit too not too much strong as Brinell. That is why I would use Rockwell test in order to check the hardness of biocomposites. Here you can see that there was a change in the indentation. It's not a spherical shape but a conical shape. Yeah, the basic thing is that Rockwell test is for lower hardness materials, and also the hardness of biocomposites is very very varying, but I think that it will be all the time in the limit of the Rockwell scale with no problem. Okay, so now after performing the fatigue test discussed earlier, we can see now a sketch of both materials. we can see how biocomposites have a lower stress, and the endurance limit is much lower than the ceramics. On the other hand, the ceramics will reach 50 million cycles with no problem. It's not a really big number. Usually, they tend to go up to 10 to the power of 7 or 10 to the power of 8 cycles. So that is a decent amount. After the apparition of cracks, obviously the stress will be reduced, as well as the endurance limit, but the number of cycles that need to be performed so that the endurance limit of the ceramics reach the endurance limits of the biocomposites tends to infinity. So regarding fatigue, ceramic is a much better option than biocomposites. Okay, so regarding the creep, um, we have discussed that ceramics are much better at creep than biocomposites. That's why the biocomposites curve is a bit switched upwards, which means that over time the deformation experienced by the biocomposites would be higher than the one experienced by the advanced ceramics. Also for stress lower than the yield stress. And here we can identify the different stages. This one is the one that's important for us, which is the elastic zone. Um, and what we can see, or we can conclude that for grip, also advanced ceramics are a better option. Now we should investigate the effects of how temperature changes in the Colorado Canyon. The temperature variation I investigated, it's between 0 and 35 degrees Celsius. That means that it doesn't go to really high temperatures, either to really low temperatures. It's an average temperature. However, um, imagine some year there's a lot of hot or a lot of cold. I have made a summary of the main characteristics. So an increase in temperature usually may reduce endurance limit of biocomposites and also increase the ductility of biocomposites. The increase in ductility is caused by the microstructure of those fibers. Higher temperatures, there will be less um, fibers entangled between each other, and uh, that would mean a higher ductility. The reduction in the endurance, it's um, is theoretical. Increasing the temperature usually reduces the endurance limit, but maybe at 40, 50 degrees Celsius as a incredible high temperature, I don't think they will be highly influenced. Then the decrease in temperature would cause the opposite to the increase in temperature. And I have not talked about advanced ceramics basically because they are highly resistant to temperature changes and they won't be affected by them. Okay, so now we'll talk about the basic design of my bridge. Okay, so basically, you can see that uh, this part simulates the canyon. The structure of my bridge is basically two or whatever the size of the bridge should be, but a number of towers and pillars as well as cables, which will be made of advanced ceramics. This is basically because they have a better compression strength. The load of the road would be directly transmitted to those pillars and cables. The cables would be in tension, but we have seen also that those ceramics work really well below their yield stress in tension. So that's why we do them of advanced ceramics. The road, where the cars would pass as well as the people walking with sidewalks, I would do that with biocomposites. That is basically because I don't think that the pressure or the load applied would be greater than the yield stress of the biocomposites, and as I just said, these the highest amount of load would be distributed between those towers and the cables. As you can see also, here's my innovation, which are some scaffolders. The construction of a bridge is usually very damaging for a natural environment like the Colorado Canyon. And that is why I think that we should use those bio scaffolders, which can be easily installed and removed. And yeah, basically, then after what was my idea, which is can be sketched here, is that in order to maintain the coherence of the landscape, we should install some biopanels uh, using some of the bioresin. So we can just paste those panels over here just to simulate the environmental decoration of the bridge. So now we can see how would the whole process be. The first would be the manufacturing of those materials. Here I included the 3D printing and also some laser cutting techniques. Then we would use bioresin to join them. And thanks to the use of bioscaffolders, we could be able to start constructing the bridge. Then we would retire those bioscaffolders, which of course can be reused for future applications. And we would cover everything with those biopanels to simulate the landscape. Finally, after constructing the road with biocomposites, I will also include some sidewalk with benches and other biological decoration for the people who wants to go through there. And yeah, here finally there's a summary of what I would do. Basically, the advanced ceramics are to support the greater loads, and the biocomposites are for environmental concerns regarding the scaffolders and also the current aesthetics of the site. And finally, talking about innovation, uh, as I just said, I would use those bioscaffolders. It would be something similar to this. They can be used with biodegradable materials such as bamboo. The basic thing is that this would be useful to avoid destroying the ecosystem, thanks to their easy installation and retirement. And finally, that they can be reused in other constructions. And when they are obsolete, because other future forms may arise, they can be easily recycled or renewed. So this is the end of my presentation, and thank you very much.